Welcome. Today we shall be discussing gravitational waves. What is gravitational radiation? Let us first remind ourselves about what is electromagnetic radiation. Maxwell's equations for the electromagnetic fields imply that the electric field and the magnetic field satisfy the wave equation which is given over there. Del squared E minus 1 over c squared d2E by dt squared is equal to 0. The magnetic field B satisfies a similar equation. Now this wave equation tells us that if we have a system of moving charges, then the fluctuations in the electric and magnetic fields propagate as waves that travel at the speed of light c. These waves are transverse and carry away energy. The radiation field, the electric field and the magnetic field associated with radiation fall off as 1 over r and not as 1 over r squared as in Coulomb's law. This is an important difference. Now, what is gravitational radiation? In a similar manner to electromagnetic radiation, if we have a collection of masses in motion, then do the variations in the gravitational field propagate as waves, just as variations in the electric and magnetic field propagate as electromagnetic waves. Are there such things as gravitational waves? In Newton's theory of gravitation, there are no such waves. That is because in Newton's theory, the gravitational potential, the scalar potential U, satisfies the Laplace equation and not the wave equation. The Laplace equation is del squared U is equal to 0. So the solution of this are certainly not propagating waves. Let us stick with Newton's theory. If you have two stars, for example, in orbit around a common center of mass, then they will do so forever. The planets will revolve around the sun forever and ever in Newton's theory of gravity. Just as two charges going around each other would do so forever in Coulomb's theory. But in Maxwell's theory, two charges going around a common center of mass will radiate electromagnetic waves. The existence of these electromagnetic waves is a direct consequence of retarded potentials. If you remember retarded potentials that we discussed in the lecture on radiation from accelerated charges. But just to remind you, I'll show you a picture that I showed before. You have a charge moving along in this direction with a uniform velocity. It is suddenly decelerated and brought to rest at x equal to 0. Inside a certain radius, the information that the particle has come to rest at x equal to 0 has propagated. Therefore, the electric fields will be radial and pointing towards the current location of the charge. Whereas outside this region, the information that the charge has decelerated and come to a stop has not yet reached, and therefore the electric field outside will once again be radial but pointing towards a future position of the charge. Now, the only way to connect these two radial electric fields, shown in blue and red, is by having a transverse electric field in the region that I'm indicating with the cursor. That transverse electric field is what we will call as a radiation field. It propagates outwards with a velocity equal to c, and this transverse electric field is what falls off as 1 over r instead of 1 over r squared. Therefore, electromagnetic waves is a direct consequences of retarded potentials of the fact that no signal can propagate with a speed greater than the speed of light. The speed of light is absolute. Now, in 1904, the great French mathematician Henri Poincaré wrote a very famous paper, which is not often read and even more rarely quoted. What he argued was the following. He realized that in Newton's theory, gravitational influence propagates instantaneously. But he knew that according to Maxwell's theory of electricity and magnetism, nothing can travel faster than the speed of light. Therefore, Poincaré said in this paper that Newton's laws need an essential modification, namely that the gravitational influences can also propagate only with speed equal to c and not greater than c. And the moment you bring in this restriction, Poincaré argued that there should exist gravitational waves which propagate with the velocity of light. Now, what is extraordinary, at least to me, about this paper was that it was pre-Special Theory of Relativity, which Einstein published in the following year. Now let's get back to gravitational radiation. Einstein's equations for the gravitational field are given here. We discussed this in an earlier lecture. Rij is the Ricci tensor and Rij minus 1/2 Gij. Gij is the metric tensor times R, which is the contraction of Rij, is equal to minus 8 pi g by c to the power 4 times the energy momentum tensor Tij. We will not pause to discuss this once again in any detail. But I just want you to appreciate that this set of equations is the relativistic replacement for Poisson's equation, which says that del squared u is equal to 4 pi g over rho. Sorry, 4 pi g rho over c. And this Ricci tensor Rij are derivatives of the metric tensor Gij. And there are 10 components of the metric tensor Gij. Now, in regions where there is no matter, that is outside of the region where there is matter, far away in vacuum, Einstein's equation for gravitation reads as follows. The Ricci tensor Rjk is equal to 0. Now, this is the analog of del squared u is equal to 0, or Laplace's equation in Newtonian theory. The above equation, like Laplace's equation, is a set of second order differential equations. There are 10 equations for the coefficients of the metric, 10 coefficients of the metric tensor Gij. Please let me repeat once again that the Ricci tensor Rjk are calculated from derivatives of the metric tensor Gij. As I pointed out in my introduction to general relativity, this equation, which is Einstein's equation for the gravitational field outside of the matter distribution in vacuum, reduces to Laplace's equation in the limit c tending to infinity. This equation will become del squared u equal to 0. But we don't want to put c equal to infinity. We want to discuss the consequences of the relativistic theory of gravitation for a possible existence of gravitational waves. Now let us assume that the gravitational field produced by moving masses is weak. In other words, it can be described in a post-Newtonian approximation. In that approximation, the metric tensor GIK can be written as GIK superscript 0 plus a perturbation HIK. Now, the first term here is just the Minkowski metric, the metric of special relativity in the absence of gravity. Now, this second term HIK is a small correction to the Minkowski metric of flat space-time arising due to the fact that there is a weak gravitational field. Why am I considering a weak gravitational field? Because that is what Einstein considered soon after he discovered his equation, because he didn't have the exact solution for his full relativistic equation that was discovered by Schwarzschild, as we discussed before. Now, in this particular case, Einstein's equation take a very simple form. Del squared HIK minus 1 over c squared del squared HIK by dt squared is equal to 0. In other words, the equation satisfied by the perturbation to the Minkowski metric HIK is just the ordinary usual wave equation. Thus, gravitational fields, perturbations in the gravitational fields, like perturbations in the electromagnetic field, will propagate in vacuum as waves with a velocity of light c. Therefore, what I'm trying to say is Einstein's theory of general relativity in the limit of weak gravity predicts not Laplace's equation, but a wave equation for the perturbations in the gravitational field arising due to the motion of a system of masses. But Einstein did not believe gravitational waves exist. This is extraordinary. The General Theory of Relativity had two qualitatively new predictions. One was the existence of black holes, and two, the existence of gravitational waves. Extraordinarily, Einstein rejected both these predictions of general relativity. He violently rejected the notion of black holes, as we discussed, and now we are talking about Einstein rejecting the notion of electromagnetic gravitational waves as arising from his theory of gravity. Why? That is because he felt that the wave-like solutions, which are the solutions of this wave equation for the perturbations of the space-time metric, is for a linearized theory of gravitation. His general theory of relativity is, of course, manifestly a nonlinear theory. Therefore, he was worried, and rightly so, that this wave-like solution of this equation, which comes from his linearized theory, may be a spurious solution. Very often it is the case that if you have a differential equation, the class of solutions of a linearized version of the theory is much larger than the class of solution of the exact theory. Therefore, it is possible that some of the solutions of the linearized theory are spurious. Einstein believed that the electromagnetic wave solutions, the gravitational wave solutions of this equation are spurious. In addition, he doubted whether these waves carry away energy and angular momentum, because if gravitational waves are the result of the motion of massive bodies, which give rise to fluctuations in the metric, then the waves must carry away energy and angular momentum. Einstein believed that these waves, solution of this equation, do not carry away energy and angular momentum. Now, let us try to understand this a little more. To repeat once again, in the presence of a weak gravitational field in vacuum, that means far away from where the masses are, the metric can be expanded to the sum of the Minkowski special relativity metric, flat space-time, plus a small perturbation HIK, and HIK satisfies the wave equation. Notice that as c tends to infinity, this equation, which is Einstein's equation for gravitation in vacuum, reduces to Laplace's equation, and there is no radiation. Like in electromagnetism, the existence of gravitational radiation is a direct consequence of the finiteness of the propagation speed of gravitational perturbations and the retardation effect. In other words, potentials have to be retarded, like in the case of electromagnetism. Perturbations in space-time, curvature, HIK, or perturbations in space-time curvature. Remember, in the presence of gravity, the space-time is a Riemannian manifold endowed with a metric GIK, and HIK are the perturbations in this metric arising due to motions of massive bodies propagate as gravitational waves. Now, it is in this sense that gravitational waves are ripples in the fabric of space-time. I'm sure you've heard popular lectures on gravitational waves, and they will describe gravitational waves as ripples in the fabric of space-time. This is what they mean. What they mean is gravitational waves are the propagation of the perturbations of the space-time metric. Now, let us go back to electromagnetic radiation. Consider a system of charges in motion, and let us expand the potential V as a power series, with the first term being dipole component. We discussed this in our lecture on radiation from accelerated charges. An arbitrary distribution of charges can be decomposed into a spherical distribution, a dipole distribution, a quadrupole distribution, an octopole distribution, and so on. Now, in the case of electromagnetic radiation, we can expand the potential where A0 is the monopole component, A1 is the dipole component, A2 is the quadrupole component, and so on. This varies as 1 over r, this varies as 1 over r squared, the quadrupole component varies as 1 over r cubed, and so on. Now this P cos theta, P0, P1, P2, P3, and so on, are what are known as Legendre polynomials, right? P2 cos theta, for example, is 3 cos squared theta minus 1, and so on. I showed you pictures of this, like wave functions of atoms. The conservation of charge forbids monopole radiation. The charge is not radiated away. It's only something about the distribution of charges which is radiated away. Therefore, there is no monopole radiation in electromagnetism. The lowest order radiation is dipole radiation, which is the second term in this expansion. That dipole radiation, if you remember, the power radiated by a charge in unit time over all angles, over all frequencies, is given by this formula 2 by 3 c cube, square of the second time derivative of the dipole moment. So I argued, if the second time derivative of the dipole moment is absent, then there will be no electromagnetic radiation, even though the charges may be moving. But we stopped our discussion with dipole radiation at that point. We could have gone back to this expression and asked, what is the nature of the radiation that arises due to this third term in the expansion, which is the quadrupole component of the electric potential giving rise to the electric field. And that is what I've shown as the second term. This is proportional to the quadrupole moment Q. Not quadrupole moment Q, but it is proportional to the square of the third time derivative of the quadrupole moment. So just as this is d double dot squared, this is q triple dot squared. Now, there is one other term which we have to discuss. Just as you could have an electric dipole component arising due to the distribution of charges, you could have a magnetic dipole component arising due to this. We already discussed in the case of our pulsars that if you have a rotating magnet, a uniformly magnetized sphere, if I rotate it, will radiate electromagnetic radiation. And that will be proportional to 2 over 3 c cube m double dot whole square, where capital M is the magnetic moment of the system of the system. So to repeat once again, this is electric dipole radiation, this is magnetic dipole radiation, and this is electric quadrupole radiation. Now, magnetic dipole radiation is extremely weak. If you examine it in terms of power of V over C, where V is the speed with which the particles are moving and C is the speed of light, it is higher order in V over C than the dipole radiation. But when the dipole radiation doesn't exist due to some symmetry consideration, you have to take into account magnetic dipole radiation. The quadrupole radiation is even weaker because you look in the denominator here, it is C to the power 5, and C is a very large number. Now, to repeat again, electric quadrupole radiation is extremely weak. But it is important if dipole radiation is absent for some symmetry considerations. Or if you remember, if I have a system of charges for all of which the ratio of E over M is the same, then there is no dipole radiation. So under those circumstances, this quadrupole radiation, however weak it may be, is important. Now, if E over M is the same for all particles, the ratio of charge to mass is the same for all particles, then the magnetic moment is proportional to the angular momentum. And since the magnetic dipole radiation is proportional to m double dot squared, since m is proportional to angular momentum, and since angular momentum is conserved, m double dot is 0, and therefore you will not have magnetic dipole radiation. So if the ratio of E over m is the same for all charges, you will not have electric dipole radiation, you will not have magnetic dipole radiation, and the only radiation you can hope to have is quadrupole radiation. Now all this is for electromagnetic radiation. Now let us turn to gravitational radiation. The conservation of mass, conservation of rest mass, prohibits monopole radiation, just as the conservation of charge prohibits monopole radiation in electromagnetism. Now, the conservation of momentum of the center of mass prohibits dipole radiation in the case of gravitational radiation. Remember, in the case of electromagnetism, dipole radiation was permitted as long as d double dot was not 0. But in the case of gravitation, the conservation of momentum forbids dipole radiation. Let me explain this in another term, a beautiful, beautiful argument, but I'll show that in the next slide. Now, why will dipole radiation be absent? We saw in the case of electromagnetic radiation that an assembly of charges cannot radiate in the dipole approximation if the ratio of E over M is the same for all the particles, because then the dipole moment is proportional to the momentum of the center of mass, and the center of mass cannot accelerate. In the case of gravitating masses, since the ratio of the gravitational mass to inertial mass is the same, there will be no dipole radiation. So let me say it again. If you remember in our lecture on General Relativity, I began by introducing the idea of gravitational mass and inertial mass in Newtonian theory. And then we argued, using Newton's third law, that the inertial mass must be equal to the gravitational mass. This Einstein regarded as some sort of a magic, unnecessary magic in Newtonian theory. But the fact of the matter is that the ratio of the gravitational mass, let's call it gravitational charge in the context of gravitational waves, to inertial mass, since it is the same for all masses, then using the same theorem as before, you can show that there will be no dipole radiation. Right? Fine. So let's repeat. Conservation of mass prohibits monopole radiation. The conservation of momentum of the center of mass prohibits dipole radiation. Therefore, the lowest order radiation in the case of gravitational system is quadrupole radiation. The lowest order radiation is due to the quadrupole moment Q, and if you work out the theory, which I am not doing, then you will find that the luminosity of gravitational radiation, or the energy radiated by the system per unit time over all directions, is equal to minus, because energy is being radiated away, is G divided by 45 times e to the power 5 multiplied by the square of the third time derivative of the gravitational quadrupole moment, Q triple dot whole square. Now I want you to appreciate that this expression for the luminosity of gravitational radiation is incredibly weak, because you have G, which is the universal constant of gravitation, coming in the numerator. That's a very small quantity. And you have c to the power 5 in the denominator. So because of this combination, gravitational radiation is incredibly weak, even if the system permits radiation to occur. And that is why it was so difficult to detect it. Now, let's look at this expression for the power radiated in all directions once again. Minus G over 45 c to the power 5 Q triple dot whole square. Now, what is the quadrupole moment? The quadrupole moment is a tensor. The quadrupole moment is a tensor. The dipole moment is a vector, E times R. Quadrupole moment is a tensor. So let's call this as Q alpha beta. In other words, can be written in the form of a matrix, where the rows and columns are to be described by alpha and beta. Is an integral of rho dV over the whole volume times 3x alpha x beta minus delta alpha beta x gamma. Now, where delta alpha beta is the Kronecker delta function. It is 0 except when alpha is equal to beta. Now, you may or may not have encountered quadrupole moment before. Let us consider, for example, 2 point masses, equal masses m, going around a common center of mass. In that case, this expression reduces to the following simple formula. Is m, which is the mass of each of those particles, multiplied by 3xij, minus modulus of x whole square delta ij. So this is the quadrupole moment. So you can look up in some elementary mathematical physics books if you would like to learn a little more. I would suggest you go to Google and look at images, type gravitational quadrupole moment or electric quadrupole moment or magnetic quadrupole moment, and look at images, and then you will see beautiful pictorial representation of the quadrupole moment. So there are 4 lobes for quadrupole moment. Now, let us consider how test particles will respond if a gravitational wave goes past them. So if I have a cork piece floating in water, and at some distance, if I drop a piece of stone, circular waves will propagate from the point where I drop the stone, And as the wave goes past the cork will go up and down as the various crests of the wave go past it. So the cork will go up and down. So in a similar fashion, let us ask, if we have two masses, 1 and 2, how will they respond when a plane gravitational wave moves in this direction? Now, because quadrupole moment is a tensor, the gravitational wave is a tensorial quantity. So, for example, if I have masses distributed all over this red circle, then the red circle will be squeezed into an oval like this. Then it will get back to a circular shape. Then it will become oval in this 90-degree orientation. Then again a circle, and so on. So gravitational wave will result in relative motions of particles as indicated in this figure. So this figure tells you in totality the principle of any kind of detector that you might build to detect gravitational waves. Please remember that when a gravitational wave passes, all you can measure is the relative acceleration of two bodies. It's the relative acceleration of the two bodies that tells you about the propagation of gravitational waves. Now, as I told you, Einstein himself did not believe when he derived gravitational wave solutions for his General Theory of Relativity in the weak gravity approximation. And indeed, till he died, he never believed the existence of gravitational waves. Now, to repeat once again, he found radiation in a linearized version of his theory. Could this radiation therefore be a spurious solution of the linearized theory? If gravitational waves exist, they must carry away energy and angular momentum. There was very serious doubts about whether gravitational waves, even though a linearized theory predicts wave-like solutions, do they carry away energy and angular momentum? There were very serious doubts for a long time. And that was settled finally only in 1957 by Hermann Bondi, whose name we have encountered before. Hermann Bondi proved this in a beautiful paper in a rigorous manner, that gravitational waves do indeed carry away energy and angular momentum. But this was still under some special approximations. The existence of gravitational wave in the full nonlinear theory of gravitation, which is what the General Theory of Relativity is, was proved only a couple of years later. And it was proved in a series of papers by Hermann Bondi, Pirani, Robinson, and Trautmann in a series of classic papers, some of them written jointly, some of them written individually. So by 1957, 58, 59, there was absolutely no doubt that gravitational waves exist in General Theory of Relativity, and that it is not due to some spurious effect of linearizing the theory. It was proved convincingly that they do carry away energy and angular momentum. But sadly, Einstein was no more. Einstein died in April 1955. Now, that still left one important question. Let's go back to electromagnetic radiation. You have a collection of charges in motion, and let's consider the radiation in the dipole approximation. The dipole approximation is a good enough approximation if you are considering wavelengths which are large compared to the size of the system, and speeds of charges which are small compared to the speed of light. We discussed this in an earlier lecture. then the luminosity of the radiation, or the energy radiated per unit time over all angles, is given by 2 by 3 c cubed times d double dot whole square. Now, this radiation is certainly carrying away energy. There is no doubt about that. But where is this energy really coming from? Surely that information must somehow be contained in the motion of charges. Now, if you remember, the way we calculated this is to calculate the scalar potential phi and the vector potential A, the retarded version of scalar potential and the vector potential. All right? R minus T by C, the retarded potential. So now we approximated that by expanding in powers of V over C and keeping only the lowest order term, and that gave us the dipole radiation. Now, if you examine this problem more carefully, expand the retarded potential for the scalar potential and the vector potential to higher order in V over C, and that's what the great Dutch theoretical physicist Lorentz did, then in third order, you discover that there is a radiation damping force. What you actually discover is that there is an electric field, square of which will correspond to the radiation. There is an electric field, and this arises in the third order in the expansion of the scalar and vector potentials in power V over C. So it comes in V over C to the power 3. So you have to expand it to that term, to that order. And that radiation damping force, Lorentz calculated, is given by this expression, 2E over 3C cubed times D double dot, where D is the dipole moment of the system. All right? So there is as a result of the motion, there is a force acting on the charges. And the charges do work against this force. And the work is given by F dot V, where V is the speed of the particle, summed over all the particles in our distribution and averaged over some characteristic time scale. Lorentz did that, and he found that the work done on the system of charges is given by minus 2 over 3c cubed d double dot whole square. Now look at this remarkable thing. The person at infinity says that I am detecting radiation, which is given by this formula, 2 over 3c cubed d double dot whole square. A person sitting near the system of moving charges says, I see that these charges are doing some work and expending a certain amount of energy. And that work done is given by this expression over there. Now, remarkably, these two expressions are the same except for minus sign. So what this means is the following. The energy and angular momentum which is radiated away and which is detected at infinity as electromagnetic radiation results in a back reaction on the system of charges, and these two perfectly match. So you could either calculate that there is electromagnetic radiation by going to infinity, or right near the system in the near zone, you can say, look, the charges are losing energy, they are doing some work. This must be going away somewhere. So this is known as radiation reaction. So only after Lorentz established radiation reaction, people really believed that electromagnetic waves must in fact exist. So a similar question was being asked in the case of gravitational radiation. Yes, Hermann Bondi has proved that the perturbations in the space-time metric do carry away as waves energy and angular momentum. But is that amount of energy and angular momentum lost? Does it correspond to the energy and angular momentum lost by the system of moving masses due to some work that it is doing? So that was a very, very hard problem that had remained for several decades, and it had eluded even giants like Lev Landau, the great theoretical physicist. Now in 1970, Chandrasekhar in Chicago and his student Paul Esposito cracked this long-standing problem. I remember this very vividly because I was a student and Paul Esposito was one of my classmates. And this was a very profound discovery. Now this gave confidence that general relativity was physically meaningful and well-behaved. This established once and for all that energy and angular momentum radiated in gravitational waves was correctly balanced by the loss from the energy and angular momentum of the radiating system. So the two matched each other perfectly. So what Chandrasekhar and Esposito did was the gravitational equivalent of what the great Lorentz did around the turn of the 20th century for electromagnetic radiation. So now you really have to believe in the existence of gravitational waves. What are the sources or likely sources of gravitational radiation? First, gravitational radiation will arise from moving bodies in binary and multiple systems. Two, gravitational radiation will arise from pulsating objects or rotating objects as long as the object is not spherically symmetric. So if I have a sphere and it rotates, it will not emit gravitational radiation. But if I put a little marble on the, stick a marble on the sphere and create a little bump, it's no longer spherically symmetric. It has a quadrupole moment, and therefore it will radiate gravitational radiation. We shall discuss this in the next lecture. Now, gravitational radiation is also expected from supernova explosions, as long as the supernova explosions are not spherically symmetric. As long as there is an asymmetry, then one does expect gravitational radiation from them. Then there are exotic theories of contemporary cosmology, which we shall discuss towards the end of the series of lectures, which predict that gravitational waves, the universe must be filled with gravitational waves produced in the very early universe, when the universe expanded exponentially. So these are the four sources that I'm aware of from which you can expect gravitational radiation. Now let us consider gravitational radiation from binary stars, because it is in such a system that the existence of gravitational radiation was first proved, as we discuss when we discuss the Hulse-Taylor binary pulsar. So let us discuss gravitational radiation from binary stars. Let us have two stars of mass M1 and M2. The relative elliptical orbits, the orbits will be elliptical around a common center of mass. Both masses will move around an elliptical orbit around a common center of mass. And in reduced coordinates, the relative elliptical orbits is described by this equation, where A is the semi-major axis of the ellipse, E is the eccentricity, psi is the polar angle, and R is the radius vector. So these are the usual coordinates, and this is the equation for the elliptical orbit. So given this, one can calculate the quadrupole moment, and one can calculate Q triple dot and use that formula to calculate the luminosity L of gravitational radiation that you expect from a system of binary stars which are in motion around a common center of mass. And that is the formula. Once you calculate the quadrupole moment, you can use this formula to calculate the luminosity of gravitational waves. Now, as I explained in the Hulse-Taylor pulsar lecture, because gravitational waves carry away energy and angular momentum, this has to come at the expense of the orbital energy and orbital momentum. Therefore, the orbit will shrink. The emission of gravitational waves produces changes in the orbit. Now, the total energy of the system E is 1/2 of g m1 m2 by the semi-major axis. This comes from Virial theorem. The total energy is 1/2 of the gravitational potential energy, and that is the gravitational potential energy, g mm over A. Now, the rate of change of the semi-major axis, dA by dt, I can bring A over here, I can bring E over there, and I can calculate dA by dt, and that is given by this expression over there. dA by dt is proportional to dE by dt, and this is the proportionality factor over here. So in order to calculate the rate of shrinking of the orbit, dA by dt, I need to calculate dE by dt, namely the rate at which the gravitational waves are being radiated, energy carried away by the gravitational waves per unit time. Now, the rate of change of semi-major axis is given by, if I now substitute the expression for dE by dt, remember, I have a system, I know the equation for the orbit, I can calculate the quadrupole moment and its triple time derivative, and therefore I know what dE by dt is. So if I substitute that expression for dE by dt, I will show you that expression for dE by dt in the next slide. I will get an expression for dA by dt, namely the rate of change of the semi-major axis. Now, I want you to appreciate that the rate of change of the semi-major axis is inversely proportional to the cube of the semi-major axis. Therefore, when the orbit is very large, semi-major axis is very large, the orbit will shrink very little. So as the orbit shrinks, A becomes smaller and smaller and smaller. The rate at which A shrinks will become larger and larger and larger. So as A decreases, dA by dt increases. Now, let's look at this expression for the energy loss rate of the binary system due to emission of gravitational waves. Now, that is given by this expression. Where does this expression come from? This is just Q triple dot whole squared. So you have to honestly calculate the quadrupole moment Q using the formula that I gave you. Q alpha beta is equal to integral of rho, etc., etc. You have to calculate that. Take the third time derivative, square it. And when you do that, this is the expression that you get. Now, E, if you remember, or epsilon, is the eccentricity of the orbit. So that function is a function of the eccentricity that is given by this expression, which you need not bother about. I just want you to appreciate that the luminosity of gravitational radiation, dE by dt, is a strong function of the eccentricity of the orbit. The more eccentric the orbit is, the larger is the luminosity, because you notice it is e squared, e to the power 4, and so on. So the radiated power is very sensitive to eccentricity. The radiated power, dE by dt, is proportional to f of E. Now, f of E is what I have shown here. F of E as a function of E, where E is the eccentricity. So as the eccentricity increases, the radiated power increases very dramatically. If you remember, for the Hulse-Taylor binary pulsar, the eccentricity was 0.6. That's why the shrinking of the orbit was very easily detectable. Now, let's go back to the Hulse-Taylor pulsar. What is plotted on the y-axis is the cumulative shift of the periastron, all right? And this is as a function of year. The pulsar was discovered in 1974, and this is 2005. If there was no gravitational radiation, if there is no decay of the orbit, then the data point should lie on this horizontal line. But general relativity predicts this solid line. You notice the data points sit beautifully on the predicted general relativistic line. And the observed change in the orbital period, p orbital dot, divided by the predicted p orbital dot for the Hulse-Taylor binary pulsar was found to be, from these observations, to be 0.997 plus or minus 0.002. So Einstein's General Theory of Relativity's prediction was spectacularly confirmed by the shrinking of the orbit of the binary pulsar due to the emission of gravitational radiation. So as I said then, the orbit of this pulsar is shrinking dramatically at the rate of 1 millimeter per year. In the case of the double pulsar, you remember a binary system of two neutron stars, both of which are functioning as pulsars and both of which are beaming towards us. It's a much tighter orbit. The shrinking of the orbit is dramatic. It's almost a centimeter per day, 7 millimeters per day. Now, why is the power radiated sensitive to eccentricity? That is because the power radiated is sensitive to the changes in velocity. Remember in electromagnetic theory, Larmor's formula, the power radiated is 2 by 3 c cubed multiplied by square of the acceleration, rate of change of velocity. Similarly, it is that rate of change of velocity multiplied by e squared that we wrote as d double dot whole square. So similarly, if you examine q triple dot whole square, the main contributor to that comes from acceleration. And the acceleration is largest in an elliptical orbit near the periastron. Okay? And therefore, more eccentric the orbit is, the greater is the luminosity. Larger the eccentricity, closer the stars are to periastron, and greater is the acceleration. Remember, both the stars are moving in elliptical orbit around a common center of mass. And so the maximum radiation will arise when both the stars are near the periastron, very close to the center of mass, where the velocity changes will be maximum. Now, what will be the spectrum of gravitational radiation? The spectrum of radiation will not be like the spectrum of dipole radiation. If you remember dipole radiation, if a dipole varies harmonically with the frequency omega, then the radiation is also of frequency omega. In this case, because gravitational wave is related to the quadrupole moment, and the quadrupole moment is proportional to the second Legendre polynomial 3 cos squared theta minus 1, in the case of a circular orbit, the power will be radiated not at the circular frequency, but twice the circular frequency. It will be the second harmonic of the orbital frequency. That is just a direct consequence of the quadrupolar nature of it. Now, for eccentric orbit, higher harmonics of the fundamentals will be present. This is for a circular orbit. So, if the orbit is eccentric, then you will have the second harmonic plus higher harmonics arising due to non-circular nature of the orbit. For highly eccentric orbit, the power radiated mainly will be in higher harmonics. This is because the radiation is emitted primarily at the periastron. These are things you have to keep in mind when you build a detector. The last thing I want to say on this subject is that as the orbit shrinks, as dA by dt increases, dE by dt will also change dramatically. Namely, the eccentricity will change. The orbit will become more and more circular. So one of the effects of emitting gravitational radiation from an elliptical orbit will be that the orbit will tend to be circularized. Now, we know that both in the case of the Hulse-Taylor pulsar and in the double pulsar, the orbit is shrinking at the rate of 1 millimeter per year and 7 millimeters per year in the case of the double pulsar. So if you wait long enough, for example, 100 million years, the two pulsars, two neutron stars in the Hulse-Taylor binary system and in the double pulsar, they will spiral in and eventually coalesce and collide against one another. The double pulsar will do it even sooner than 100 million years. Just before the two neutron stars merge, there will be a burst of gravitational waves because the orbit will become more and more the periastron distance will become smaller and smaller, and therefore there will be a burst of gravitational radiation. So the idea was, let's build detectors to detect gravitational waves from merging neutron stars and perhaps other sources that I listed over there, supernovae, gravitational waves from the early universe, and so on, and in particular, merger of two neutron stars, because such a system had been found, and we find that system to be shrinking, and we know that the shrinking is due to emission of gravitational waves, because the shrinking of the orbit agrees precisely with the prediction of general theory of relativity. So the gravitational wave detector known as LIGO, it's a laser interferometer built by Caltech and MIT in collaboration that finally found gravitational waves in 2015. Now, I do not want to trivialize this by spending a couple of minutes about this detector. If you remember, neutrinos were predicted by Pauli in 1930, and it was discovered in 1956, 26 years of hard work. Raymond Davis first found the neutrinos from the sun in 1968, but the smoking gun was only found in 2013, some 45 years later. So in a similar fashion, the design and development of this laser interferometer took almost 30 years. It was a culmination of the highest level of technology development, engineering, and theoretical physics and modeling. And this effort was led by the great astrophysicist and general relativist Kip Thorne at the California Institute of Technology. So Dr. Sushant Kunar will give references to several talks by Professor Kip Thorne, and you must listen to his wonderful, wonderful talks, and also about the development of this laser interferometer. So I shall not say anything further, because that would be trivializing an effort that lasted almost 30 years. Now, let us consider some reason it's not working. Well, that is supposed to be a movie that shows how two black holes spiral in and eventually merge. Doesn't matter why the movie is not working, but let's look at what the theory predicts of such a spiral in. So two black holes are spiraling in, they come closer and closer, and finally they merge. Then the gravitational waves that you expect from such a merger will have this kind of a waveform. Now, what is shown here are two curves really, a gray curve and the red curve. The red curve is the theoretical calculation using general relativity, and the gray curve is the reconstructed template with which you would detect such gravitational wave. So the theoretical prediction is if two black holes or two neutron stars spiral in and emit a burst of gravitational waves, this will be the signature of the gravitational wave. Well, I'm sorry, this is also not working. This beautiful video shows how, as you can see this, go to the LIGO website. This is actually both those, the previous one as well as this one, are taken from the LIGO website. You go to the LIGO website, you'll find many videos there. They're really beautiful and worth looking at. Now, on the 14th of September 2015, almost 100 years after Einstein published his General Theory of Relativity, a gravitational wave burst precisely as predicted by theory was detected by the LIGO interferometer. Okay, the LIGO interferometer is there at two different sites, Hanford and Livingston, and both of them detected these gravitational waves. And modeling suggested that the gravitational waves were from the coalescence of two black holes, each roughly about 30 times the mass of the Sun. So 100 years after Einstein's theory predicted the existence of gravitational waves, notwithstanding that Einstein rejected this for nearly 40 years after he discovered it, gravitational waves were finally found. It was a triumph, let me say once again, of engineering, technology, and theoretical physics. 2 years later, on 17th of August 2017, this burst of gravitational waves was detected from two neutron stars which are about to merge. Soon after the burst of gravitational waves, there was a burst of gamma rays from the same place. And after the gamma rays faded away, there was an afterglow at longer wavelength, X-rays, ultraviolet, visible wavelengths, all the way going down to radio wavelength. Now, here it is. What is shown in the central panel is the burst of gravitational wave. And what is shown on the top and bottom are gamma ray bursts with two different gamma ray telescopes. This is the upper panel is the Fermi Large Area Gamma Ray Telescope, and this is the integral telescope. Both of them show a gravitational burst with a small time difference, and that turned out to be an extremely important thing and a bonus indeed. Because gravitational bursts have been known for nearly 30 years. Some are of galactic origin, but most of them are extragalactic at cosmological distances. Now, we now know that at least some of the gravitational bursts are associated with neutron star mergers. Indeed, nearly 30 years before this event, it had been predicted by astrophysicists that the merger of two neutron stars will result in a burst of gravitational waves. And so this was a beautiful confirmation of the theoretical prediction of nearly 30 years ago. So here is the gamma ray burst, and here is the burst of gravitational waves. I shall say some more about this when we discuss the synthesis of elements in one of the later lectures. Now, what happens when the two neutron stars really merge? That's an interesting, as yet unsolved question. In the August 2017 event, LIGO could not follow the gravitational burst till the neutron stars actually coalesced. That is because as the neutron stars came closer and closer and closer, they'll be going faster and faster and faster, and the gravitational waves will be at a higher and higher frequency. And the present version of LIGO could not have detected those high-frequency gravitational waves. Therefore, the current frequency response of LIGO implied that the gravitational wave chirp is faster and faster, that's a chirp, could be followed only till an orbital separation of about 1,000 kilometers or 100 stellar radii. So the two neutron stars were apart by hundreds neutron star radii, still quite far apart. But LIGO was sensitive enough to detect the gravitational radiation. But if it could detect higher frequency gravitational radiation, then one would have been able to detect it closer and closer, with the neutron stars closer and closer to one another. Why? As the two neutron stars approach one another, they will tidally distort each other. So tidal distortions will appear on the neutron stars. Now, if these tidal distortions can be studied through their signature on the gravitational wave chirp, then that will tell us a great deal about the equation of state of matter in the interior of the neutron star. So please remember that the neutron star crust is very stiff. How stiff it is or how soft it is still a matter of debate. So the tidal deformations will give us a handle to analyze working backwards about the equation of state of neutron star matter. So, will the result of the merger be a black hole? But that depends upon when the two neutron stars merge, whether the resultant mass is larger than the maximum mass of a neutron star or less than the maximum mass of the neutron star. As we said before in an earlier lecture, according to our best estimate, using the most sophisticated equation of state, the maximum mass of a neutron star is probably around 2 or 2.5 solar masses. In which case, if two neutron stars of 1.4 solar mass each coalesce, then the resultant thing will be a black hole. Or will it be a black hole surrounded by a torus of neutron matter, like the rings of Saturn? If that is the case, then you can expect exciting nucleosynthesis of heavy elements like gold and platinum in this neutron torus around a freshly merged double neutron star system. So the interesting question arises where elements like gold and platinum synthesize in such mergers of neutron stars. Now, if the two neutron stars have mass of about 1.4 solar mass, the resultant mass may be less than a maximum mass of the two rotating neutron stars. Remember, the maximum mass of a rotating neutron star is significantly higher. I gave you the number for it, calculated by John Friedman and his collaborators. But there are possibilities that even if the resultant mass is less than the maximum mass, it would still collapse and form a black hole due to some dynamical instabilities. So, exciting times are ahead. When there is an upgrade of LIGO in the next year or two, one will be able to follow the coalescence of neutron stars till they actually merge, and that will tell us a great deal about the synthesis of elements like gold and platinum, as well as about equation of state of neutron star matter. So for this heroic effort of building LIGO and finally detecting gravitational waves, Professor Barry Barish at Caltech, Professor Kip Thorne at Caltech, and Professor Rainer Weiss at the Massachusetts Institute of Technology were awarded the 2017 Nobel Prize for Physics. I strongly recommend that you listen to lectures, semi-popular lectures by Professor Kip Thorne. They are sheer intellectual treats. Now, as of March 2022, a couple of months ago, the LIGO, Virgo, Kagra collaboration, these are the names of 3 gravitational wave detectors, have so far detected 90 gravitational wave bursts. It's like everything else. It took a long time before somebody could run a mile under a minute. After that, everybody and his grandmother can do that under a minute. So it took 100 years to find gravitational waves. And then within a couple of years, we have found 90 such gravitational wave bursts. So read more about these exciting developments in the references that you will find in the description below this video. And in the next lecture, we will switch gears. We will discuss millisecond pulsars. Till then, thank you for your attention.